Hello, this is the demo for keras TensorFlow advanced tutorial. And so in the earlier demos we have seen how to use keras and TensorFlow for basic operations, but now in this one we will be creating a proper neural network and a production ready code. So yeah, this is the initialization, and for this we'll be using GPU. And yeah, so this advanced gradient tape patterns. So in the earlier demos we have we have calculated the gradient by ourselves, and manually back propagating those values. But in this case we will use the gradient tape functionality of TensorFlow, which computes which computes the gradients automatically. It goes back and computes the gradient descent, and gives you the output. So yeah, so these are now nested gradient tapes, which is for higher order derivatives. So yeah, again the Jacobian and Hessian computation will come here. So first first level derivative, we just pass it like this, dot gradient function, and then we do another second derivative, we find it like this, and the third derivative we find it, pass this value, and then again x, and that is how we get the third derivative of value. So that is how it it computed with these so for one gradient tape, we did it for 3 times, we had to call it thrice, and we had to pass it again and again. So yeah, that is how we got the high order derivatives. Now let's see, look at the Jacobian computation, which is the first order partial derivatives. Excuse me. So yes, so this is our the TensorFlow looks like. It has a value, this x of 0 exponent 2, x of 0 multiplied by x of 1, then sine of x2. Now let's say we want to compute the Jacobian. So Jacobian is first order derivative. This is just finding the derivative once, and that will be excuse me. So now I'll just show you the output. So yeah, so this was the vector, right? x to the power 2, x1 into x2, and sine of x3. Now the this particular column will be derivative of x1, this will be x2, and this will be x3. So we'll see how it looks now. So this was x1, so x1's derivative for this will be 2x1. So that is how we got this. Now for this one, derivative of x1 is x2, so we got x2. Here nothing is there, the whole thing will be considered as constant and it will become 0. Then now this is for x2, so here there is no x2 value, so this will be 0. Here it will become x1, and again same here, 0. Now for these, as x3 is not present in both of these, we will count it as 0, and sine derivative of sine is cos, so that's why cos x3. And then based on the true values, we got the this expected Jacobian matrix. So now for Hessian computation, we are first finding out the gradient, and then we are doing the Jacobian on top of it. So Jacobian is second order partial derivatives. So excuse me. Yeah, so we can call, we are calling it like this. Now again we got these are the values, the original equation. Sorry, no, that was not there. Yeah, this is the original equation. So this is the first order derivatives. So this is first one is based on x, uh, derivative respect to x, which is 2xy, and this will become constant, so nothing. And then second is with respect to y, which is x square plus 3y square, and we got 3y square here. This is the first order derivatives, basically Jacobian. Yes. Then Hessian is again partial second order derivative on this. So for this, as I mentioned, this will be x and this is y. So here it will be 2y, and this will be 2x plus, as there is no y, it will be 0. So yeah, only these two values will come. And now with respect to y, we will get 2x, and this will be 0, and this will be 6y. So that is how we got this matrix, and these are the values with true values. So yeah, that is how we compute the Hessian matrix, derivatives, and yeah, this is, sometimes you need to define custom gradients for non-differential operations like argmax, and for numerical stability, or for custom background passes. So yeah, this is how we can create the custom gradient. We are just calling the norm and setting a condition to of our custom value, and that is how we will get the values. So here we want to clip it to normalize to 1. So whatever we value got, it is 3 and 4, we have to normalize it to 0 to 1. So it will do the computation and gives the output to this. Yeah, and which is within the range. Now this is straight through estimator. So it is used for binary or discrete operations that are not differentiable again, and for quantization in neural networks. So yes, so here we are straight through round. This will round the number to its nearest integer, and straight through sign is it will retain the sign of the value, negative or positive, and yeah, that it will that is how it will work. Then we have gradient accumulation, which is it is useful when the batch size is too large for GPU memory, so you want efficient batch sizes. So you have to provide the batch size, and it will create efficient batch size based on batch size and accumulation steps, and it will then do the create those batches and then do the computations on top of it. So yeah, so this is for compute gradients for mini batches, and accumulate sum or average over n steps, and apply accumulated gradient once, and yeah, the effective batch size is mini batch into number of steps. Now let's build neural network from scratch using the primitive operations, not the high level API. So like we did in the PyTorch as well, we will just we'll give the batch size, we'll give the input and output weights size, and kernels H and W will be passed, and as it's a convolutional layer, we need some padding as well. So this will take care of the padding and how we want our output to look. We are initializing it over here. And once that is done, we are using now Einstein summation to do this operation. And it will we are passing the patch and the kernel, and it will give us the output in this format, and which is our convolutional tensor. Once we get that, we'll do the operations on top of it. So we are calling it, we are passing the values, the kernel, stride, padding, um, and it will create a convolutional layer from very scratch. So this is how it's built under the hood. But most of the time we don't have to build from from scratch, but it's really good to understand. So when the use case is you have to deep dive and make changes at the fundamental level, you can just then use this and create make your changes according to you. So now we got the convolutional. Now we will do the max pooling from scratch. So again we will take the input, pool size and the stride, and for each pool size there will be a pool size by pool size window, take the maximum value. Excuse me. So yeah, that is what is happening over here. It is extracting the window and max over spatial dimensions, and we get our max pooling from scratch. And same we will do for batch normalization. We will create it from scratch using the basic primitive methods available in PyTorch. And this is the normalization equation we want to apply, and this is the scale and shift. Now let's create the layer from scratch. So for layer, layer normalization, so normalize across features and not batch. So this is used in transformers because works with any batch, and no running statistics needed, and each sample normalized independently. So excuse me. So we will this is the initialization of epsilon, normalized shape, gamma, beta, and the formula for mean and variance, and the normalization, and how do we want to scale and shift. Now that is done, we are these are the input, these are the expected output, or how the mean is calculated. Now once that is done, this is how the layer normalization from scratch looks like. Now again we are doing the dropout from scratch. So dropout is randomly zero at neurons during training. So yeah, so we do that so that the expected value remains the same during the inference. So that is what is happening over here. We are randomly selecting few values and setting them as 0. So that is also done over here. Now let's create the full dense layer from primitives. So we will initialize our in features, out features, our bias, and we will initialize the weights here, and bias is also initialized. Now once that is done, we will this is the formula we want to apply. This is our forward passes formula, where we want our input to be matrix multiplied with W, and then we want to add our bias to each element, and a result should be the output passing through an activation function. That should be our output. That is pretty much what we are creating over here. and this is what the input was, input shape, output shape, bias, and this, and this we got the value as. Now let's create a convolutional layer from primitives. So again, for convolutional layer we need the in channel, out channel, kernel size, stride, padding, activation, and bias. All these values are passed, they are initialized, and those values are all these values are kernel weights, and the input will are created over here, and then we are passing it to this TensorFlow's convolutional 2D function with the input, the kernel, stride, and padding. And once we get the output, we are adding the bias to it, and again we are passing it to an activation function and then returning it. So we'll see how it looks. Yeah, this is how the input size was. Now let's create a complete CNN built using only primitive layers. So right now we just did this. We just created a layer and outputted its value. But now let's create a multi-layer. So there's one convolutional ReLU max pool, convolutional ReLU max pool, flatten, dense. So this is what we want to do. So we will just create. We need two convolutional layers, that is for sure, right? So we are initializing those. Then we need H and W, and once that is done, we need two dense layers, and yeah. So now we are creating two max pools, and one dropout from scratch. Dropout is there, okay. ReLU, and we need ReLU as well. ReLU and max pool, sorry, softmax is also created, and yeah. So this is where we are defining the layers, what we want to do. So yes, so the variables whatever we are creating, we are adding it into this variables list, and then this variables list will be executed one after another, and that is how we have created a convolutional network of this, where it calls this layer, then this, and then this. You can see convolution 2D, this layer, then dense layer, and then dense layer, and then it gets the output in this format. So now custom keras layer. Now we have built it from very primitive functions. Now let's create it using the inbuilt functionalities which keras have. So yeah, so we can, again, like PyTorch, we can inherit it from this layers.layer. So we will initialize it, we'll do the super to get all properties of the parent class, and define bias, activation, initialize units, activation, bias, and then we'll define our kernel, our bias, and then we'll do the output. What we want is, we want to do a matrix multiplication of input with the kernel, and then add the bias and pass it to an activation and return the output. So that is done. When we call this, it will initialize the layer, and let me just yes, uh, initialize the layer, and then this will trigger the build, and this will get in this will start working, and once that is done, the layers will work, and we'll get an output for it. So this is how the config looks like. Now we will create a custom layer, which is an self-attention. So self-attention is basically this formula. So this is mostly used in transformers. So to understand uh, what this particular thing is relating to, or based on the previous and post words, what this word is, or word, or what that particular input is trying to say. So it takes care of the relation between post and pre input as well. So here we are, this is the formula for that. Then again, so we have to do a softmax with a q, k, and we need a v as well. So that is what is happening over here. We are creating wq, wk, wv, and wo, which is weights for each matrix, and then here we are doing that matrix multiplication which we have to do. Once that is done, we are for few we have to do a transpose as well. All the operations are happening over here, and then we are getting the output and the attention weights. So this is how it is implementation it did. And here we are using the spectral normalization, which is spectral normalization. So again, spectral normalization wrapper for layers, it constrains the spectral norm, which is the largest singular value of the matrix, weight matrix, and this is used in GANs to stabilize training. So yeah, basically it's normalizing your weight vector. So yeah, that is what is happening over here. We are building, we are doing the matrix multiplication, and we are calling the normalization. Now again, this is for the residual block. So learning the residual is easier than learning y directly. So this enables training very deep neural network. So yeah, that is also is possible using TensorFlow and or PyTorch. So I have actually explained this in the previous video. I will just, yeah, I think that is pretty much all. The operations which we did in the PyTorch are also here, are similar. Just you have to call the formula is like mostly the same. We just have to call the functionalities one after another, like we did in PyTorch. Yes, that is pretty much it. Thank you so much.